we will start our problem with an equilateral triangle. Then, using the base of this triangle, we will inscribe a half circle as you can see on the sketch. Next, on the upper remaining empty part of our equilateral triangle, we will inscribe a full circle with the area of 6. The question is, can we somehow calculate the area of our semicircle? So if you guys want to try this problem out for yourself, you can pause the video as always and then come back and check my solution. Alright, so let's solve this problem together. So for this problem, I'm not going to label any vertices because I think that we can get away without it. And I'm first going to take a look at our inscribed full circle with the area of 6. As you know, the area of any circle equals pi r squared. And since the area of our circle is 6, we will get that pi r squared equals 6. We can simplify by pi, and we will get the following. Then, from this, we will get that the radius of our circle equals the square root of 6 over pi. Alright, so I'm also going to label this radius as small r on the sketch on the left, as you can see, and while we are here, let's also label the radius of our big semicircle as capital R. Let's save this value for r because we're going to need it later. Now let's rotate the radius of our circle to the point of tangency, and let's do the same for the radius of our semicircle. If we do this, we can use the tangent of a circle theorem, which states that if we have a circle and a tangent line, and if we pull a radius to the point of tangency, the radius will always be perpendicular to the tangent line. And we can use this theorem in our case. As you can see here, we also have the radius which goes to the point of tangency, and our tangent line is actually the side of our equilateral triangle. The same thing applies for the circle on the top. So this radius must be perpendicular to the right side of our triangle as well. Alright, so now we know that our big triangle is an equilateral triangle. So this means that all of its acute angles are 60-degree angles. And if we pull a height of this triangle, it will bisect the angle at the top into two 30-degree angles. But furthermore, this height will actually pass through both centers of our two circles, and this is due to the fact that symmetry applies for an equilateral triangle. Alright, so why is this important? Well, take a look at the newly formed green triangle on the top. This triangle is a right-angled triangle with an acute angle of 30 degrees, which means that the other acute angle must be 60 degrees. So this is actually the famous 30, 60, 90-degree triangle, and we can use the property of this triangle. Of course, I have used this triangle many times on this channel, but it never hurts to remind ourselves again about those properties. So, the sides of 30, 60, 90-degree triangle are always in a relation of 1 to square root of 3 to 2. And we're going to use this fact. Now, you can notice that I have labeled the sketch on the right the same as the sketch on the left, so you can easily follow what I'm doing. And if you take a look at the sketch on the left, our small triangle has the side of R, which is in between the angles of 60 degrees and 90 degrees. So this means that the side between the angles of 60 and 30 degrees must be equal to 2r, and this is actually also the hypotenuse of this triangle. Well, now the same thing applies for this big green triangle with the side of capital R. Since this is the similar triangle to our previous, hypotenuse must be 2 times capital R. Now let's clear our image once again. And the name of the game here is to find the relation between the small r and capital R. If we are able to do that, well, then we are going to probably solve this problem with ease. So let's try to do that. First, let's rotate the small radius vertically down and the big radius vertically up. If we do this, we will form this really nice straight line along the height of the triangle. And if we simplify our sketch, it will look something like this. From here, we can conclude that the overall length of this line is 2 capital R, and it consists out of segments of capital R, small r, and 2 small r. So we can write this down as an equation. We can now work through this by grouping the common terms, and we will get that capital R equals 3 small r. And this is exactly what we are looking for, the relation between capital and small r. Now, we can find the value of capital R by replacing the value of small r, which we got earlier, and we will get something like this. Alright, so now let's clear our image once again, and remember, we're looking for the area of the semicircle, and the area of this semicircle equals to 1/2 of pi capital R squared. So we can just substitute the value of capital R and get the following. And this looks terrifying, so we're just going to put our last term on a square and get something like this. And from here, we can simplify pi and pi, and we can also simplify 2 and 6 to get 3. And we will get that the final answer, or the area of our red semicircle, if you will, equals to 27 squared units, and this is our solution. Well, I really hope you guys enjoyed this awesome problem. If you did, do not hesitate to leave a like or subscribe to the channel for more content like this in the future. If you know a person who loves problem like this, please share this video with them, and if you found another way to solve this problem, write it down in the comment section as you always do. And until next time, see you guys and take care.